Kia ora and welcome to video 15 in the series Delightful Differentiation. Happy Friday. Short problem today. We're going to show that the tangent to this function here, y equals square root of sine of x, at the point where x equals pi over 3, about here on the curve, never intersects the curve again. And if you're reading that going, that's a bit weird, tangents usually don't intersect their curves again. All you need to do is think about a cubic. A cubic where it twists. You could easily have a tangent where it goes across and cuts the curve at a different position when the cubic bends the other direction. So give that a go, and happy Friday. So it pays with this problem to have a quick look at the graph first. The square root of sine of x there is shown on the domain of 0 to pi. However, sine x repeats itself, and so therefore the graph repeats itself. The graph is periodic. So here's the graph, and we've got a tangent there at x equals pi over 3, and we can see that it doesn't intersect the curve anywhere else because it's below that segment of the curve, and it's above the next segment of the curve in the positive direction. So that's enough to prove that it doesn't intersect again if we can explain the periodic nature of this function. In other words, it repeats itself every 2 pi because sine x repeats itself every 2 pi. Okay, so let's do the maths. We just need to find the equation of the tangent first and then find its intercept. So equation of a tangent means that we need to differentiate first up. So y equals sine of x all to the half, y dash half sine x to the minus 1 half times by the derivative of sine, which is cosine. It's the chain rule. We can tidy it up if we want. Y dash is equal to cos x over 2 square root sine x. Now we need to sub in x equals pi over 3. We're looking for the gradient at that specific point. A quick estimation there. It's a positive number. Alrighty, cosine of pi over 3, draw our special triangle. Pi over 3, not to scale because pi over 3 is actually 60 degrees. But that side there is root 3, that side there is 1, and that's 2. It's half an equilateral triangle. So y dash at x equals pi over 3. Cosine of pi over 3 is a half. And we're dividing by 2 lots of square root sine x. Square root of sine x, or sine x, is root 3 over 2. So that there is our gradient. And of course we then need to evaluate that. We could leave it in exact form, but it's a little bit messy. So if I just type that in, we've got 0.5 divided by 2, also divided by the square root of root 3 over 2. Okay, and that comes out to be 0.2686. Just going back to Desmos just to check if that seems like a sensible number. Let's put in a graph that has exactly the same gradient. So straight line of gradient 0.2686. I've rounded that to 4 decimal places. Yep, that looks good. That's a parallel line. And then we can use y equals mx plus c, or we can use the tangent, the equation of a straight line, y minus y1 equals mx minus x1. We've got our m, 0.2686, and we've got our x1, y1. It's a specific point on the curve. X equals pi over 3 is the x value, the y value is the square root of sine of pi over 3, which is the square root of root 3 over 2. Okay, so let's work out what that one is. Root 3 over 2, square root it again, 0.9306. So we've got y minus 0.9306. Just make a bit more space here. 0.9306 equals m times x minus pi over 3. Sorry, I'm inconsistently working between surds, which I've rounded to decimals, and I'm leaving pi over 3 in exact form. no real reason for that. And then we want our x-intercept. Okay, our x-intercept will make y 0. If you do that, y being 0 minus 0.9306 divided by 0.2686 and then add pi over 3, you end up getting minus 2.4175. There's going to be potentially a little bit of tolerance there for rounding. And then we go back to that. It means that our tangent comes down here and our x-intercept of the tangent is minus 2.4175. And then we just need to argue or give a valid reason as to why the graph there starts after or more negative than minus 2.4175. So you're going to say something like the range of the function is clearly from 0 to 1. So 0 less than or equal to y less than or equal to 1. It's not possible to get y values bigger than 1 because the sine of x is bounded with a maximum value of 1, and then the square root of that is bounded with a maximum value of 1. And then you could talk about the domain. And you could say that the domain is, it's not just 0 to pi. Obviously that domain there is shown from 0 to pi. But then we've also got the next one from 2 pi to 3 pi. So in general, we're going 2n pi to n plus 1 pi, where n is an integer, n belongs to, oopsies, I was going to write I, n belongs to z, the integers. And we just say that minus 2.4175 is not in the domain of the function. Therefore, it's not cutting the curve again. Okay, the tangent only touches once at that position, and then it's not possible because it hits the x-axis before the function root sine x kicks off again. Anyways, hopefully that made sense to you. Pretty nice little problem there. Not overly difficult. You're just finding the equation of the tangent, but I guess the reasoning at the end is what matters the most and what makes this problem slightly left field. Catch you next week.